3D. But baby steps first, right? So suppose we have a vector. We have a couple of vectors, okay? One vector I'm going to throw is this. 1, 5. Let's say we have a vector here at 1, 5. There. Okay, I'm gonna make this thing a blue vector. Okay, so this is, I'm gonna name this thing R naught at time 0, if you will, right? And this thingy is 1, 5. So far so good? Okay. Now let's have another vector, and which is at 5, -4. Okay. From here and 5 and -4 is right there. I'm gonna name this vector R1. Let's say 1 second later. And this is 5, -4. Okay, these are usually coordinate spaces, right? And you're taught just to be coordinate spaces, but they're really vectors and they're equivalent. Coordinate and component notation of vectors are really equivalent, aren't they? And now I want to figure out R1 minus R naught, also known as delta R. Get it? So let's throw another vector here. And vector subtraction, if you remember, looks like this, doesn't it? Make that red. So this vector is delta R, okay, which is R1 vector minus R0 vector. You know what I'm saying? Say yes. Okay. Let's compute this thingy. Okay, if we compute this thingy turns out to be, is it just 4, -9? Say yes. Okay. Now, I will give you a choice. I mean, I'm going to do it both ways. But do you want to see the algebra derivation first, or do you want to see some physics like motion, velocity, time derivation first? Your choice. I'm doing both.
I guess algebra first.
Algebra first. Okay, let's do algebra first. So let's see if we can figure out the equation of this line. Okay, point slope form. Point slope form requires a point and a slope, correct? So let's figure out the slope. Slope here is y2 minus y1 over, I know I feel a little silly teaching you this, but there's a value. So this is -9/4, right? Do you see -9/4 here and here? Slope and this are highly related, right? Because they are both directions. Slope gives you a direction and this vector gives you a direction. You know what I'm saying? Okay, and then let's say we use the starting point. So what we have is y minus 5 is equal to -9/4 and x minus 1. You with me? Okay, so that's the equation of the line going through this red vector. At t is equal to 0, t is equal to 1, and so on. Let me change that around a little bit. Y minus 5 over -9 is equal to x minus 1 over 4. Still the same thing? Couple of things that should remind you. Number one, it looks like conics, doesn't it? It does look like conic if you bring it to one side, right? In fact, everything is a conic. I'm not sure if I did this with you in the past, but let's say this is 3 and 4. What's the equation of this line? Really quick. You believe it? Let's check that out. What's the x-intercept of this thingy? When y is equal to 0, 4. Y-intercept when x is equal to 0, 3. Bang, huh? Oh my. Right, okay. So this is kind of similar thing. However, also, does it remind you of this thing called symmetric equations from your pre-calc book? Yeah, these are symmetric equations. These are the most worthless things in real life in physics, but hey, mathematicians are obsessed by it, so let's learn it. So I can separate it now, this, and call it t, and then the other one, and call that t. So far so good. So that's the same thing, but I'm creating this parameter because we are trying to get parametric equations. You know what I'm saying? So these two are equal. However, this thing tells you that x is equal to 1 plus 4t, right? And this thing tells you y is equal to 5 minus 9t. And these are your parametric equations. Okay, now let's see if we can feel it. Could we have just started with this instead of going through all this algebra? Let's see. When t is equal to 0, what's my original position, the coordinate? 0, 0, 1, 5, 1, 5, right? 1 second later, I want my new position to be 5, negative 4, right? So if I just put 1 plus 4, 5, 5 minus 9, negative 4, then if I plug in 1 here and here, then I get 5, negative 4, right? Ah, so why do we even go through all of this when we can just write it, right? Ah, okay, let's talk physics. Has your physics teacher given you this yet? Okay, actually you have seen this, right? Okay, this is 0 for now. Straight line, so there's no acceleration, constant motion. You know what I'm saying? Okay, I'm gonna write this as a vector notation. Okay, so I'm gonna change the color. Say, if I write it like this, x, y is equal to 1, 5 plus 4, negative 9 t. Do you agree it's exactly the same thing? Because you distribute t, and then you add, and you get this. You know what I'm saying? So this is a vector equation equivalent of this parametric equation now, isn't it? You with me so far? And this is what we call our vector function R. Okay, I'm going to show you a slight difference of, like, it's the same thing, but vector function is like this. We go back to this. I'm going to draw that vector function somewhere here, right? Let's say that's a black. Now, vector function is, we have our vector starting here. So tail is always at the origin, and then arrowhead tells you where this particle motion is. You get it? That's a vector function. So in 1 second, you want this thing to move from here to here. You get it? So I'm just going to leave it somewhere here, any arbitrary point, and call that R of t. It moves. Get it? It describes that motion. Okay. Now, then, in order to develop this into 3D, let's talk about velocity. Velocity is, of course, derivative of this now, isn't it? But just since it's a constant motion, there's no acceleration. Can we say it is delta R, delta x used to be. Now we are in 3D, delta R over delta t. Say yes. Okay, delta t is 1 because we are saying this is from when t is equal to 0. Let me write it. T is equal to 0 here, and this is when t is equal to 1, isn't it? So our denominator is 1. What's my numerator? Well, delta r. We calculated that delta r up. Where did we do it? Oh, here, right? So that is 4 and -9. How about that? Does that ring a bell from last year? Because in the 2 years ago pre-calculus class, you calculate this thingy, one minus the other called v, subtract the coordinate, and you didn't know why they are called v because it's velocity vector. You get it? And then you use your initial coordinate plus your v times t. So this is really r of t is equal to your r0 plus v t. And do you see this is exactly the same thing as that in now multiple dimension now? How about that, huh? So exactly same thing as physics. Eventually this will grow into this in your physics class. And then plus 1/2 at squared. A being the acceleration vector, of course. Shall we practice this on 3D now? Yeah, okay. So 3D, suppose there's a line. Say kind of like that, any random line, okay? Suppose there are 2 points on the line. So you're given 2 coordinates. And that one coordinate is this. And then I'm gonna call it vector notation 7, 5, 4. And the other, this is to make it exactly same as your Dropbox note. And then 12, 17, and -3. I don't know why anybody came up with that kind of number, but okay, that's back then. What that means is really in this abstract drawing, it's perfect. There's some 3D coordinates somewhere, right? That's not as good, right? X, Y, Z here. Okay. So this vector, this is a vector function now. So this vector right here is that vector. You get it? And 1 second later, this vector will move over like that. You with me? So this vector is r naught, and this vector is r1. Say yes. Now we need to calculate the direction, velocity vector. Okay, I'm going to do that with red. Velocity vector will be that, right? I'm going to write it. V here is, of course, r1 minus r0, right? So we have 5, 12, and -7. Still with me? So far, so good. Now, from there, we can just say our vector function r of t is equal to r0 plus vt. And if you want to write component notation, this r0 is 7, 5, 4. You see why I want to use a vector notation instead of coordinate? Because to use it like that, it literally is a vector, okay? Plus, and then we have our velocity 5, 12, -7, t. You get it? And if you want to create a parametric equation, this becomes 7 plus 5t, and 5 plus 12t, and 4 minus 7t. How about that? So that gives us our parametric equations. X is equal to 7 plus 5t, and y is equal to 5 plus 12t, and z is equal to 4 minus 7t. How about that? Good. Now, if you want to convert this to symmetric equation, you see how to create this now? I mean, to me, I mean, that's good enough, or that's good enough, but like, I really don't care too much about parametric equations, but mathematicians are obsessed by this and symmetric equations, right? So this thing tells you x minus 7 over 5 is equal to t, and this thing tells you y minus 5 over 12 is equal to t, and this thing tells you z minus 4 over negative 7 is equal to t, right? Say yes. So equating those, we have symmetric equation x minus 7 over 5 is equal to y minus 5 over 12 is equal to z minus 4 over negative 7. How about that? Now, this is not even an equation. Equations should only have two sides, not three. You get it? So it's like, this is one of the most useless thing there is in physics, in real life, but mathematicians love this for some reason. Okay? Whatever. Okay. Should we put this into 3D grapher and observe the space? Yeah, let's do that. I mean, I got a machine that does it. And then these days, actually, Desmos can graph even too. Really? Huh. Okay. Okay, this is my vector function graph. I'm gonna change that to yellow color so you can see. And then this is how I do 3D vectors. Is equal to another 3D vectors. Okay, so this is really one vector, but written in a matrix way. And then this first one was 7 plus 5t. And second y was equal to 5 plus 12t. And then third is equal to, what was it? 4 minus 7t. Whoa, why did it change the color? Let's zoom. Well, the other way. Do you say the spaceline segment? It's only displaying 0 to 1, but if I change this to 0 to 2, why is it 0 to 2? I don't know. 0 to 10, for example. What am I doing? Okay, 0 to 10. Negative 10 to 10. Am I changing the wrong parameter? Yep, I was changing the wrong parameter. Okay, this was my t. 0 to 10, then it becomes this longer, starting from t is equal to 0 and extending it out. So we can actually have an equation of line segment by restricting this domain t. Get it? And then while we are here, shall we take a look at some space curve? Yeah. Say if we make this thing not so linear, for example, if I make this thing square, ready? Do you see this is curvy parabola? It curves towards the y direction and everything else is linear. Oh, we can play this game. And let's make this thing cube now. Oh, right. Play with t value from negative 10. Space curve. You get it? And this is the equation of the space curve. There is no one equation. Like best you can do is that symmetric, which is not even an equation, or parametric, also known as vector function. This is the only way we can do 3D curves. Okay, so get really familiar with this thing called vector function. And then, do you know what's coming, we'll take derivatives of these. Second derivative, which is velocity and acceleration, and all of that beautiful things, and still apply.